very, very empirical science. And so the question is, how do we do better empirical science of deep learning? And this obviously is about eventually informing our theoretical understanding and as well as our ability to sort of engineer these kinds of systems better. One of the perspectives on this that I feel like I got from David Duveneau when he was in my lab along with my student Dougal McLaurin is the idea of building microscopes. So in other fields like physics and biology, if you have like a deep empirical question, there's a system you want to understand better, then you are heavily motivated to build a way to analyze that system better. Literally build a microscope, literally figure out a new way to perform an assay, or build a telescope to look at some remote object you care about, and invent new sort of instrumentation. And I feel like it's really helpful to frame some of the problems we ask about our systems in terms of building microscopes. Okay, and so the microscope that I want to sort of tell you about today is a microscope for very, very large matrices. And the reason this is an interesting microscope to build is because we care about the spectra of really big matrices, about the eigenvalues of them for a variety of different problems. In the case of deep learning, we want to ask questions about the Hessian of the optimization problem, right? So maybe you have a neural network that's going to have like tens of billions of parameters in it, right? Huge parameter spaces. And we want to reason about how hard that optimization problem was, how many different solutions there are, how the hell are these things like ever optimizable given how non-convex they are. Like there's a lot of questions we actually don't understand empirically, where we can study things at kind of small scale. And David has done some of this as well, thinking about using sort of tiny little problems where you can maybe compute the Hessian analytically and do sort of diagonalization on it. But how do we actually examine these very, very large, sort of very, very large systems that we actually see in practice? And this is a lot harder because we can't just diagonalize a 10 billion by 10 billion matrix, right? We can't even represent it, much less do some sort of cubic algorithm on it. So we want to be able to tackle these kinds of problems and understand, where are the saddle points, like are we really getting to minima, how sensitive are these problems to their parameters and so on. These are properties of the eigenvalues. But we also want to we might also ask questions about very big graphs. As a sort of, where there's this entire area of spectral graph theory. We have giant graphs, really big adjacency matrices, Laplacians, and we want to be able to interrogate those to ask questions about conductance or how the number of triangles, number of communities, and so on. And this kind of thing also arises in like many-body systems. So one thing that is sort of near and dear to my heart is using machine learning to tackle computational chemistry problems. And there we're often dealing with density functional theory and approximations to it that involve inevitably sort of reasoning again about very, very large matrices where the eigenvalues have specific sort of physical interpretations. Okay, so that's what I want to talk about today. And what I'm going to do is tell you about ways to tackle this problem by telling you about two tricks that I think are totally awesome from different communities from the late 1980s. And then we're going to plug those together and kind of twist it up just a little bit to wind up with unbiased estimates of different interesting things you might want to know about really big matrices. And I'm going to call these implicit matrices. Implicit matrices are where you can't represent it. All you can do is interrogate it via matrix vector products. And in fact, in the case of deep learning, you probably can't even actually do a matrix vector product. You can just get an unbiased estimate of a matrix vector product because you're going to have some mini batch type situation, right? But you can also think about large-scale algorithms for sparse graphs and how those would let you do these kinds of products because it's kind of an edgewise operation, but you're not going to be able to build this big matrix explicitly. Okay, so that's kind of the name of the game here, is thinking about really big matrices. So let me just kind of write that here. So we're caring about some big matrix A, and all we can do is choose some vector that we're going to multiply this guy by. And so we can look at vectors like that for some x that we get to choose, and maybe we only get an unbiased estimate of that thing. And it's hard because we can't represent A, and we can't, and it may be the case that we only again get sort of mini batch type estimates. So the first trick I'm going to tell you about is what's called the randomized trace estimator. Okay, so the lens I'm going to sort of use for this is the idea that if we can do what are called sort of generalized traces, we can answer a lot of the questions we'd like to be able to ask about really big matrices. So that is, I'm going to talk about quantities where we're going to take the trace of some matrix function applied to the matrix A. All right? So if F is like a matrix log, then this gives us an estimate of the log determinant. But we can think about other kinds of things as well. So the functions we'll talk about for F are going to be basically functions of the eigenvalues. And so we could imagine thinking about other kinds of things like indicator functions or sort of asking questions about the moments of the spectral density and other kinds of things where you apply a function to all the eigenvalues and then sum them, right? And this is kind of what we're going to be doing here. And we're going to wind up with unbiased estimates of these kinds of things. That's the name of the game. Okay, so 2 tricks that I think are awesome and that everyone should know about. The first is a randomized trace estimator. Yeah. Let's just assume that these are symmetric matrices. They don't necessarily have to be positive definite because sometimes we're going to want to ask questions about things that have negative eigenvalues. What's that? Yes, they are real. Some of the things I'll talk about would generalize, but in general, machine learners don't care about complex numbers. It appears. So, all right. So here's a very cool little trick, which is that if we have some matrix A, and we generate a vector x that's from just like a spherical normal, zero mean, and any covariance, and then we form a quadratic form, the expectation of that is the trace of A. Raise your hand if you already knew that. Okay, cool. So this is pretty easy to prove because you can just sort of apply the usual kind of like trace trick type things. So if we think about what this would be, we're going to have we can always write this when we have scalars. We can always write this guy like that, right? So it's trace of a scalar. And then we can apply everyone's favorite permutation trick, right, to the trace. So we can do this thing, right, where we sort of swing things around. And then, because trace is linear, we can write trace of the expectation. And then A pops out, right? Because it's not random. And we have chosen this guy such that this is the identity, right? So then we just wind up with trace of A. I'm showing you this because it also reveals that there's a much more general class of x's for which this would work, in particular Rademacher random variables, and anything that has the properties that this outer product of the random variables is identity. Okay, so if that's true, then you're in business. And so this is a really cool trick. It means that if we have some big matrix A and we can access it in this sort of indirect way, then we can estimate its trace. Now traces don't sound that hard, but actually they're still kind of hard to get to for like really big deep neural networks and things. One of the things that's really cool, and by the way, this is I think generally attributed to Hutchinson in 1989, but then there's been it's been used in a variety of other ways kind of since then. One of the things that's really cool about this is that it has a blessing of dimensionality. So we all have curses of dimensionality usually, but in this case, the bigger the A is, the faster this is going to converge. It's just central limit theorem essentially, because it's just going to hit more stuff whenever you're summing over more things. Whenever you do this little estimator, and so this is kind of the first trick, and there's some nice theoretical work on bounding this, and Rademacher variables are a little bit better than Gaussians, but you can imagine kind of general classes of this and so on. In the case of Gaussians, you can also reason about it in a different way by just thinking about if A is diagonalizable, then you would have this kind of like rotation, diagonal rotation, and hitting a spherical random variable with a rotation still has the same marginal, and so then it's just hitting a diagonal thing. That doesn't work for the Rademacher case, but it's something to kind of, that's kind of a useful thing to know. So that's trick number one.
Can I ask a silly question?
Yeah.
So x transpose ax is cheap to calculate for a realization of x?
So once you have done this, right, we get that thing, and now it's just an inner product with x again.
I see. Yep.
Right? So I'm assuming that I can that if I can do that, then I can dot it with something else cheaply. Yeah.
Can you give like a super simple example where you would use this?
I'm just about to keep so a super simple example will be if you wanted to estimate the log det of something big, using kind of where this is going to be matrix log. So hang around and I'll show you how we could use this for really big things, like counting. Okay, yeah.
So the classical dimensionality only works if none of your eigenvalues dominate, right? If one of the eigenvalues is
Fair enough. Yeah, no, that's right. That's right. Yeah, I mean, I'm just saying in general, if these are kind of like, yeah, if this is like a really kind of obnoxious matrix, then or it has kind of like one big value buried in it somewhere, then it's not necessarily going to help to make it bigger. That's right. I'm kind of making structural assumptions about A being kind of like dense, I guess. Like, yeah. Other questions? Okay, so that's trick number one. Really cool. Trick number two. Is from a completely different community, and it's called the Poisson estimator. And I'm guessing that on the order of 2 people in the room have heard of the Poisson estimator before. So this is kind of attributed to, I think this is attributed to Wagner in like 1987. So again, it's kind of an older trick. I learned about it from reading a paper by Omoros Papaspipopoulos from like 2009. And it solves a problem that I feel like when you sort of take undergrad statistics, you learn is impossible. And yet it turns out to not be too impossible. So here's the situation. We have a quantity, let's say we have a quantity y. And we have an estimator of y. Let's call it y hat. So we have some randomized estimator guy that has the nice property that it's unbiased. Okay? Unfortunately, we're not interested in y. We're interested in e to the y. So what we really want to know is something else, say z. Everybody knows that in general, if I just take my y hat and x-bit, I'm not going to get the right answer, right? So it turns out, though, that for relatively well-behaved functions, in particular analytic functions, you can fix it up and make an unbiased estimator for z out of unbiased estimators for y. Everybody already know that? Yeah, okay. So here is an example of how to do this. So the reason it's called the Poisson estimator is what we're going to do is we're going to draw an integer, k, from a Poisson distribution. Some parameter that is just a free parameter lambda, all right? And then what we're going to do is we're going to form a random product of a bunch of y hats. So we're going to write down an estimator z hat that is going to be equal to our e to the lambda multiplied by a product of k y hats. So these are independent y hats drawn from whatever our little estimator here is. Okay? So that's going to be a random quantity we get. The expectation of that is z is e to the y. And it's unbiased. So, I mean, that's the definition of unbiased. So this is a really cool little trick. And you can convince yourself of this by just writing it out. So if we just say, what's the expectation of this guy z hat, right? And if we remember that the Poisson PMF is lambda to the k divided by k factorial times e to the negative lambda. So if we write this guy out, then we see that we get this sum. I'm going to say a sum over j equals 0 to infinity of this PMF j so that's the probability that we get a particular k, and when we get a particular k, we do this product. 1 up to j of this guy, right? So y hat divided by lambda. Oh, sorry. That's important. Okay, so what's going to happen? If we have a product of a bunch of independent random variates, then that's just then the expectation is just is actually the product of their expectations. And so we're going to wind up being able to rewrite this as same sum over j, but now we have lambda to the j factorial. Now we're going to get j of those guys, right? So that's just going to be y to the j divided by lambda to the j. So that cancels out, that cancels out. And now we get this sum from j equals 0 to infinity of y to the j divided by j factorial. And we should recognize that as the power series for the exponential function. That's crazy, right? Like, how could that possibly work? Well, I mean, it doesn't really work, but it does. Yeah.
Naive question. If I have a data set, I calculate y hat. How do I do this? I don't get multiple estimates of y hat.
Yeah, you need to be able to get multiple estimates of y hat.
Do you use a bootstrap, or what do you?
Yeah, so if you can construct a randomized estimator by like subsampling data, that's one way to get it. Or maybe you have maybe the estimator is like some kind of like other kind of estimator where you get to generate the randomness. So maybe it's more like a randomized algorithm and less like a data subsampling thing. The variance on this can be kind of obnoxious. People have been excited about it recently for exactly the reasons that David was just talking about, which is that if we can easily get unbiased estimates of log likelihoods, and the question is, once we have those, how would we fix them up to get a valid Markov chain Monte Carlo algorithm? This is one way you could imagine doing that.
So you're focusing on the bias in these things. Like what do you have like sort of error bounds, and how does that depend on lambda?
Okay, so in this case, I'm using this as kind of an example, but really this trick is not the trick that I want to emphasize. It's that this is just, it turns out, doing randomized function approximation via importance sampling, right? So let's sort of generalize that a little bit, and then we can talk about specific cases where we can bound it, right? We have this knob we can turn to reduce the variance with lambda, but it can still be obnoxious for all the reasons that importance sampling can be obnoxious. So more generally, if we have an analytic function, right, what that means is that if we have some function we care about, it just means that we're going to be able to write it in something that looks like this. And we could do other things as well. We could do like Chebyshev polynomials and so on. And so when we see something like this, even though this is kind of like Calculus 101, if we sort of put our like Monte Carlo hat on, we could imagine actually importance sampling this guy, right? Where we would instead say, let's form an f hat of x, where we have some proposal distribution pi, and now we're going to say aj. We're going to draw an integer from pi. So pi is a distribution now over the natural numbers, and we form an estimator like that. And just because it's importance sampling, that'll be an unbiased estimate of our function at x. The variance may be a disaster, right? Depending on, just like it sort of always can be, if we choose pi poorly relative to the sequence of AJs, right? But we can look at like some specific cases, like for example, we can look at like the natural log, and there it's kind of particularly obnoxious with a slowly decaying tail, but we can choose distributions like the zeta distribution that also have comparable tails, and then we can bound the variance within the sort of radius of convergence of the original series, basically. Okay? So this is kind of just all, so even though this, at least when I first saw this, this looked like magic to me, right? But it's just doing this with the exponential function and the Poisson proposal distribution. Yeah.
So, is there some sort of simple condition on AJ and IJ to make sure that you get the reasonable estimate?
There is unfortunately not a simple condition that I have been able to identify. Generally, the kind of condition that we would expect to guarantee it to be well behaved is if basically if the ratio here has some upper bound, right? So that is to say that you never get into a situation where you choose a really sort of deep J with vanishingly small probability and it blows up. The result, exactly like when you're doing importance sampling, if your proposal distribution has lighter tails than the target, then occasionally you're going to wind up with giant weights and you could have infinite variance. So this suffers from exactly the same pathologies. The good news is that it's just the natural numbers, and so if you're doing this trick, you're probably able to interrogate the A's in a way that maybe would be easier than you could in the sort of like general inference case.
I mean, F must have a convergent power series.
Yeah. It doesn't. You can't do this better than you can do this. The point is that, you already know something about convergence of these guys. Okay, so there's two different tricks. That trick, though, what's interesting about it is that we can generalize it to the obnoxious term, which is sort of holomorphic operator calculus. All that means is that you can take this whole thing and do it for matrices. All right? And that is to say, if you have a function that you're going to apply, you're going to generalize some analytic function that you care about to matrices, then essentially what you do is write out the power series in just the same way, but now you're going to do matrix powers instead of scalar powers. And what's really nice about that is that it turns out that all you're doing when you do that is applying your scalar function f to the eigenvalues of the matrix. Do you believe me? We can kind of reason about this by just saying, okay, if I have something I care about, A, and I can diagonalize it. And then I raise A to some power, right? Then if I raise it to, say I square it, then I'm hitting it with this guy again. And these guys are just the identity, sort of by construction. And so then this thing just boils off to that, and lambda is diagonal, so this is just raising all those entries along the diagonal to that power. Okay? So we can take this then and take our favorite function f applied to matrices, and now we can importance sample these matrix valued functions for some analytic function we care about. So I think you can kind of maybe see where I'm headed with this, right? So now what we can do is we can take this trick for expanding into randomized power series. So we're just choosing one power. And then we can combine that with this trick. And we wind up with an unbiased estimate for some f. And then even if we have to do the kind of slightly more complicated thing where we generate the sort of randomized y's from many batches, say with a giant deep neural network, we can still push it through. Okay, and because the x's that we're using to do this part are independent of the randomness we're using to do this part, then you can convince yourself that you'll wind up with unbiased estimates of the overall thing. Okay? So that's kind of the main, so that's what I was saying. It's a couple of tricks from the 80s, but if we glue them together, then, and kind of generalize them a little bit, then we can see that we're able to estimate in an embarrassingly parallel way interesting properties of like giant deep neural networks. There's a couple of other kind of things that we can do here that are sort of interesting to think about. So one thing, for example, is to observe that when we do this randomized power series, so what we're literally going to do, just to describe the actual algorithm I'm suggesting, so you decide on what function you'd like to apply to your eigenvalues, you come up with your favorite power series for it, and by the way, just as a sort of like one note, this thing only converges if the operator norm of x is within the radius of convergence of the original analytic function, or the original power series. So you come up with the power series that you care about, and you're now going to draw from your proposal distribution, get a random integer, draw an x that you're going to do Hessian vector or matrix vector products with, hit it j times, and then you're going to compute the inner product with your original, back with your original x. That's going to give you a scalar that you then weight with aj and divide by the probability that you propose that j. That's now an unbiased estimate of the result. Okay? So like I said, you could use this. So if you were willing to call approximations to indicator functions, for example, an analytic function, or you're willing to write down a sort of like a Chebyshev approximation to something like a function maybe that looks like this. So modulo things like the Gibbs phenomenon, where you sort of wind up with wonky approximations near the edge, then we could ask questions about, we could count how many eigenvalues are in this epsilon ball. Right, so if we think that small eigenvalues are sort of interesting, or the number of small eigenvalues is interesting, or like near zero is interesting for the hardness, say, of an optimization problem. Okay, the other thing to observe is that I talked about how what we're going to do is hit our random, we're going to hit our random x with our matrix a bunch of times. But when we hit it a bunch of times, that means that actually we're doing all the work of computing all the intermediate terms out to some point. And so what we could do is actually come up with a different version of this, in which what we actually do is not sort of the vanilla importance sampling thing, but we observe that we're going to have a randomized truncation, and we correct, just like with importance sampling, but with the probability that we would propose that truncation. Okay? And this is like very familiar to the sort of numerics community and the way people have thought about this previously, because there you would say, okay, well, if I wanted to do this, then I like the convergence rates of Chebyshev polynomials, so I'm just going to run out to some point, and then that's where my error is going to be, right? Well, this lets us do also truncation, but by making it a random truncation, then now we get an unbiased procedure. And maybe I mean, and it's not so much a value statement about whether or not you like to have sort of like high probability tight errors or unbiased algorithms, but depending on your taste and what you want, then this is a kind of a way to do that through randomization. And the downside is, it turns out, surprisingly, that so let me just write that out sort of to make it clear what I'm actually proposing. So if we do this, we're choosing an integer and jumping to that point in the series, and then just choosing that one term in the series for our whole approximation. But if we're doing that with the whole sequence of matrix vector products, then we're going to have done all of the intermediate work to get there. So we can kind of do the right correction to use that whole sequence. And that basically looks like this, where our new estimator is going to be basically, instead of just fx, we're now going to actually have a sum up to whatever sort of integer we drew. Let's say it's k, of the a zeros the AGAs divided now by the probability that we would have, of all the sort of times that we're going to hit that thing.
So you've changed the proposal.
So it's the same proposal distribution, but if you think about it, so now you're drawing an integer, and the question is how many times are you going to hit, you need to account for all the different times that you would hit, say, like item number 3 in the series on the way to item number k, right? And so if you sort of add that up, then you always hit the first one, and then with probability 1 minus probability of the first one, you hit the second one. And so then you can sort of like correct for that, and now you can see that you have this like randomized truncation where you're correcting for where you truncate, like the probability you would truncate at that particular location. Strictly speaking, it seems like this should always be better, but it turns out that this does not always have lower variance than the naive thing. And I don't have yet sort of interesting results on like when exactly you would always do this instead. So there's a couple of tricks for estimating what I think are kind of like hard problems that I hope will help us do the science of asking questions about like 10 billion parameter models and help us understand their sort of, their properties a little bit better, ultimately leading to a better theoretical understanding of these things, as well as kind of interesting questions about graphs, interesting questions about sort of big quantum systems and other things. And 90% of what I've told you here is not new, but it's an excuse to tell you about 2 tricks that I think are really fun. So thanks for listening.
We have time for some questions. I want to also add, thank you, Ryan. Ryan stepped in spontaneously when there was a last-minute cancellation, so we are extra grateful, and this was very riveting. So we have time for a couple questions. Yep.
So I guess one question is that you have this big matrix, and if they want to compute the trace, you can always do it using n orthogonal vectors, right? So that kind of
That's true.
bound on how many tails in that series you would like to take. So do you have some sort of idea when that would give you a lot less than that?
Yeah, so this is a good point. So just to, so everybody can hear. So you could calculate the trace by doing 10 billion orthogonal vectors, right? But the hope is broadly that we'll get much lower variances much sooner, right, than doing that. But we can imagine worst case scenarios like the one you described earlier, where really there's just sort of like some sort of spike living out in the matrix somewhere, and maybe we won't see it unless we do that.
Some sort of condition, or like clearly it cannot always be true. There must be some
So
sort of
yeah, so there's 2 different things going on. So one of them is the convergence rate of this kind of thing, which there are variance bounds depending on properties of A that I wouldn't be able to recite for you now, but this is like relatively well studied. And then there is the very flexible sort of possible range of good and bad outcomes depending on F and what you engineer as pi. And so there's like F's for which we would expect this to converge very poorly, right? Where the truth is that we need to see very many, very, very many elements of the sequence to have a reasonable estimates. And this doesn't, and I don't have a condition to give you for that right now. But the reason is because we don't generally have these kinds of conditions for importance sampling. But one can always dream. I mean, we could prove the variance for particular cases, right? But I don't have a condition under which it will always work. So like I can derive the variance for like log, for example. And I'm optimistic that I can derive the variance for sort of like indicator function type things. But there's a lot of analytic functions out there.
What are some examples of data sets where you really want to compute the trace or some function of the trace?
Well, so I mean, the motivation here is the question of like, how bad is your saddle point at some point in optimization of a giant neural network, for example, right?
You've converged locally and.
Well, I mean, or you've stopped training, or maybe you're at some intermediate point in training, and there's a lot of sort of folk wisdom about what's going on with local minima versus saddle points and so on. And the question is like, how do you validate any of that folk wisdom? How do you understand any of these systems? And asking questions about these giant matrices is not something that is.
So how can you resolve that by computing the trace? Sorry, I didn't see the connection. That's a good point.
Yeah, okay, so we have this giant Hessian, and I want to know how many positive versus negative eigenvalues I have.
Oh, that's a much more sensitive question. Right? Whether there exists a negative eigenvalue.
But we could ask that question if we could write down an F that told us that was counting the number of negative eigenvalues. Right, because the trace of that will count the number of negative eigenvalues for us. Believe me?
Well, I'm not sure such a function exists, but but no.
Well, I mean, the indicator function exists. The question is, can we approximate it reasonably well with, in a way we're happy with a power series? And the answer is that people do it all the time, but you get this, but the penalty you pay is this Gibbs phenomenon, right? Which is that if we approximate functions like that have discontinuities, then you wind up with kind of like wiggles, right, near the edges. Okay.
Thank you, Ryan. Break till 4, then Emily Fox.